So how would you use the chi-square test? Was it statistically significant or not? Did anybody dare to do it? What do you think? You think 13 suns in a row is unlikely to happen by chance?
I think it's unlikely, but it's just like an outlier. Not necessarily significant.
Okay, so maybe it's very unlikely by chance, but maybe, what's the probability of having 13 suns in a row? Totally separate question than whether or not the observed meets expected. It's something like you've got a 1 in 2 chance of having a sun, and then the next kid you also have a 1 in 2 chance, and the next kid you have a 1 in 2 chance. So it's 0.5 to the 12th power. So it's like millions or billions in one chance of having that many suns in a row by chance. So is this different than what we'd expect to see? So what was that? 13, so we observe. How do you set up a chi-square test? We need observed values and we need expected values. So what are our observed values? How many different categories of individual are we looking for? How many different phenotypes are we counting? 2. We've got males and we've got females. So we observed, what was it, 13 sons, no daughters? Man, I'm glad I didn't grow up in that. That's a lot of males. A lot of testosterone flowing. So what are the expected values? How do you calculate how many expected offspring we would have expected by the rules of nature? If you have 13 kids, how many do you expect to be male and how many expect to be female? 6.5. No, you're absolutely right. This is not the time, by the way, to round. Even though, don't round, even though you're tempted to, because what the hell is a 6.5 person? Right? You can't have 6.5 kids. It's true. It's not biologically meaningful. Why do we not round? There's a critical part of the chi-square test here that means we should not round. What would happen if you rounded both of those numbers? 6.5. So we've got a total of 13 observations. We need to have a total of 13 expected observations. So if you round 6.5 and 6.5, you'd round them both up to 7, and then you'd have a total of 14 expected kids, and that doesn't match. So you wouldn't round this to 7, because then you'd have an expected value of 14 total observations, which doesn't match there, and we wouldn't be able to do a chi-square test. So even if it's not biologically relevant, use decimals if you calculate them as such when you calculate the expected. Okay. So we expect an even sex ratio, 50-50 boys and girls. Okay, how do you set up the chi-square test? We want to ask, are our observed and our expected values the same, or are they different? What's the formula? Observed minus expected squared over expected. Good. Well, at least some of you memorized that, which is good because we'll be using the chi-square test a lot. So we do observed, say boys, 13 minus 6.5. Square that. Divide it by the expected value, 6.5. Okay. Is that it? So then, what else? We have to, right, so we've done one of the two categories. We've done males so far. So we also have to add the same term, observed minus expected squared over expected, for females. 0 observed females minus 6.5 expected. Square that and divide it by expected for girls, which is the same as for boys, 6.5. In this case, that sums to 13. It won't always, just in this example. What's the number 13 in terms of the chi-square test? What do we call this number? When you do the chi-square test, we do all of the equation, we calculate a total number. It's the chi-square test statistic. And again, that's what's down here in this table. So these values in the bulk of the table are the chi-squared test statistic values. So we need to find where number 13 lies to figure out whether or not whether the observed and the expected values are different or not. But what else do we need to know? We've got chi-square test statistic value. We need one more piece of information. Degrees of freedom. Okay, number of degrees of freedom, which is the number of categories. We've got two categories in this case, males and females. So degrees of freedom is number of categories minus 1. So in this case, 2. We've got XX individuals, boys, or XY individuals, boys. We've got XX individuals, girls. Subtract 1 from that. So that gives us 1 degree of freedom. So we're going to be looking in this line of the table where it says 1 degree of freedom on the left. So 1 degree of freedom, look across, find where our chi-squared test statistic value is. Where is it? 13, down here somewhere. So off the right side of the table, if you have 1 degree of freedom and you have a chi-square value of 13, you're way over here. 5, 6, 7, who knows where 13 is. What p-value is that associated with? Probability value. Where do you get that information? Where in the table?
Is it less than 0.05?
Right. So you look up from that number. So 13 lies in here somewhere. You look up here in the header, and that tells you the p-values. So in this case, 13 corresponds with a p-value that's less than 0.005. I'll tell you what the actual p-value is of a chi-squared test statistic of 13, but what does it mean? That's the most important thing. P-value that's really small. Is that good or bad? What does it mean when you have a really small p-value? Are the observed values, so we've got two choices. That either means that the observed and the expected values match, they're statistically similar, or that the observed and the expected values don't match, that they're significantly different. Really small p-value. What's the threshold p-value? What's the critical number where you say if it's bigger, it's one thing, if it's smaller, it's another? 0.05. So this is the threshold right here. If it's bigger than that, we have one thing. That's the observed and the expected values are the same. And if it's on this side, if it's a small p-value, that means that the observed and the expected values are significantly different. What does that mean in this case? Expected 6.5 boys, 6.5 girls. We observed 13 sons and no daughters. They're significantly different. The p-value is less than 0.05, which means that in this case, this family breaks Mendel's laws. There's significantly more sons than daughters based on what you'd expect. It could still just be chance. I'm not saying that we can conclude that there's anything medically wrong with either of the parents. But the observed and the expected values are significantly different. Any questions about this process? Bless you. So this is how we use this for determining whether or not genes are linked or not. You take an observed number of offspring, like these 4 values we've been looking at for what seems like months now. And we have to calculate what first? We've got an observed number of individuals with 4 different phenotypes. We want to know, is this a 9 to 3 to 3 to 1 ratio? Is it? Doesn't look like one. But we want to know with statistics, because it's kind of pointless to set some sort of arbitrary threshold. I could ask a bunch of you, I should ask all of you to tell me if that's different or not. Some of you might say, it's close. Some of you might say, no, those are definitely different. So as scientists, we pick a specific threshold. It has to be quantitative. There's any number that will tell us whether or not, that we can all agree on, that will tell us whether or not those numbers match our expectations or not. That's the chi-square test. It's quantitative, it's not subjective. This is a common measure that all scientists around the world agree on to facilitate scientific discussion, essentially. So what are the expected values? We have an expected ratio. That's based on the Punnett square. We expected to see 9 to 3 to 3 to 1. Those 4 different phenotypes. So how do you calculate the expected values from this? How many purple long flowers should there be? What percentage? We've got 16 total parts from this Punnett square based ratio. 9 plus 3 plus 3 plus 1. There's 16 parts to that ratio. So 9/16 of the plants should be purple and long. 9/16 of what number? Exactly, the total. So we observe a given number of plants. It'll change depending on the situation, the scenario. So we expect 9/16 times 427. About 240? Okay. And then for purple round and for red and long, those would be 3/16 of 427. Which I got to be 80, which is a third of 240. So 9/16, 240, 3/16 is a third of that, 80. The same is true for the next one, which should also be 3 parts. So you expect 80 there as well. And then 1/16 of 427. 26.6. I'm just going to round it 27. That still totals 427. So even with rounding, we get the total number of observations matching the total number of expectations. That's critical. If they're not totaling the same thing, the chi-square test won't work properly. So now how many times do we have to do observe minus expected squared over expected? How many times do we have to calculate that? Yeah, 4 times. We have to do that formula for each combination of observed and expected. and observed and expected, and observed and expected, and observed and expected. You do this calculation 4 times with those 4 different pairs of numbers. And then you find out what the chi-square test statistic value is, which in this case is, I'm going to give you the punchline. I'm going to ask you to do this on your own with a different question for next class. So chi-squared value is 219. So for example, that would be 296 observed minus expected squared over expected. Then you'd add that to the next clause, and the next clause, and the next clause. You'd add those all up, and that would total 219. So plug in all the numbers, do the math. What does it mean? Okay. Big chi-square value, 219. How do you interpret it? What's the next thing we need to do?
Graph the degrees of freedom.
Yep, chi-square value, step 1, number of degrees of freedom.
3.
We've got 4 categories, 4 different phenotypes. Yep, so 4 minus 1 is 3 degrees of freedom. So what's the p-value associated with a chi-square value of 219 with 3 degrees of freedom? Well, our table goes in that line, 3 degrees of freedom goes to 12. 219's in the astronomy building, in the Downing planet, or farther than that maybe. What's the p-value? Is it big or is it small? You look at what the p-values do when you move from left to right. You go from basically 1 to, we're already in the significant range when we get to this column, less than 0.05. Way over there is infinitesimally small p-value. Tiny p-value. In this case, holy cow. So 3 degrees of freedom, chi-square value of 219, p-value of 2 times 10 to the minus 47. Right, 47, decimal point, 47 zeros, and then you get your number. Crazy small. Statistically significantly different observed and expected values. P is less than 0.05. Therefore, the observed and the expected values don't match. P less than 0.05. So what did that tell Bateson and Punnett about their cross that they set up between the pink and the red flowers and the round and the long pollen? They didn't observe what Mendel predicted, what he would have expected. They didn't see a 9:3 to 3:1 ratio. What does that tell us? Why are we using this example? What are we learning about? Linkage. This was the evidence, the observed and the expected values didn't match. This was evidence that maybe the genes that are controlling pollen shape and flower color are on the same chromosome. When the observed and the expected values of the ratios don't match. When you don't see 9:3 to 3:1 in the case where you do, expect it. So significant differences from what you expect to see often indicates linkage. Sir?
You want to use 0.05 or 0.005 to see this statistically significant?
So we scientists have settled on 0.05 as sort of the threshold value. Sometimes you'll see people say 0.005, that's highly statistically significant or very significant. So it's basically, for me and for most scientists, it's 0.05 is the magic number. If it's bigger, it's not significantly different. They are not significantly different. If it's smaller than that, you conclude simply that the numbers that you're looking at comparing are significantly different. But the choice of 0.05 is arbitrary. I mean, some human picked that number. It's not like there's something magical about 0.05, and if your p-value is 0.051, that somehow it's amazingly different from having been just a little bit smaller p-value, 0.05 or 0.049. It's arbitrary, but it's a threshold that we've established as a scientific community, and we agree on. So the difference between 0.051 and 0.049 is not much, but the way we interpret data, it's actually a pretty big distance. But there's nothing particularly special about 0.05 other than we agree that that's important. Which, when you think about it, doesn't really sound that scientific. But so today we move on from chi-square tests into using a particular sort of cross, a test cross, to determine how far apart genes are. So we can use chi-square tests to tell if genes are on the same chromosome or not. Beyond that, we can calculate how far apart genes are on the same chromosome. So this is where we're heading today in next class as well. This is how we do this. So mapping genes that are unlinked. So these are genes, semicolon. Two genes, A and B, on two totally separate chromosomes. So you can cross them together. By the way, what are the P0 generations gametes looking like here? So the parent on the left produces, say, sperm that have what? What would you write in that spermatid? What's its haplotype? Yeah, it's got to have a big A and a little b. Okay. And the other parent produces an ovum that's little a, big B. Okay, so those are the parental haplotypes. And we've seen by doing these chi-square or the Punnett squares that you expect to see this sort of ratio when you set up this F1 cross. What's the genotype? What do we call this genotype? The big A over little a, big B over little b, the F1. This guy right here on the left, the F1 individual. That's what? This. It's a particular type of cross. We've got a dihybrid on one side. This is a tester individual. What does that make this cross? Dihybrid test cross. Dihybrid test cross. This is the one cross that you will be using a lot to do genetic mapping, to ask how far apart two genes are. Dihybrid test cross involves a dihybrid and a tester. So this is, a lot of you have been coming up after class and asking me about, is there a name for this particular type of genotype? Like when it's heterozygous at one locus but homozygous at another locus, there aren't really that many special terms for genotypes. We have pure breeding individuals, where every locus you're looking at that you're interested in is homozygous. We've got monohybrids and dihybrids, right? Like a dihybrid here. Di, two loci, hybrid, heterozygous at both. What's unique about the tester individual's genotype? This is essentially the last special term we have for a genotype. What's true about a tester? It's homozygous plus, what sort of alleles is it homozygous for? Recessive. So a tester is homozygous recessive at all of the genes we're interested in studying. So how did I come up with this list of genotypes? 250 of each of those 4 different genotypes. What does the Punnett square look like for a dihybrid test cross? Indeed. So what's special about a tester individual? How many haplotypes does a tester individual produce? Just one. Well, one haplotype. It has to be little a, little b. That's why we use a tester individual. It's pure breeding. It makes a gamete that only contributes recessive alleles. There's no capital letters in any of its gametes, all lowercase. We'll see why that's important in just a minute. So if you were going to set up a Punnett square, this is definitely a Punnett rectangle. Because the dihybrid, or sorry, the tester, only occupies one row. It only makes one gamete type. So here's the tester gametes. It only contributes little a's and little b's to the next generation. So what do I write across the top here? The gametes produced by the dihybrid. We did this already, right? Big A with big B, big A with little a with big B, and little a with little b. Remembering that we're talking about mapping up here in the top unlinked genes. So we're going into this knowing that these genes are on separate chromosomes, hence the semicolon. And it's this Punnett square, when you fill it in, that gives us this ratio of offspring. Expect to see a 1 to 1 to 1 to 1 ratio, equal numbers of those 4 different genotypes. In this case, I happen to make them total 1,000 individuals. So we have 250 of each of the 4 different genotypes. So we expect from a dihybrid test cross, we expect a 1 to 1 to 1 to 1 ratio of 4 different offspring, F2s. So we expect chi-square test, we're going to expect to see equal ratios of 4 different types of offspring from a dihybrid test cross. Any questions or concerns? Trying to find out how far apart on the chromosome are genes A and B. Make a dihybrid, cross it to a tester individual. We expect this. We're going to see how many of those 4 different types do we have. Do they show up in a 1 to 1 to 1 to 1 ratio or not? Back again, 2 slides. Of these 4 types of genotypes, which ones are the parental types and which ones are the recombinant types? So what we do is we look up here at the parental gametes. We saw a parental gamete type was big A, little b, and the other one was little a, big B. So those are the parental haplotypes, wrote up here. So to detect whether or not genes are recombining or not, if they're on the same chromosome and how much they're recombining, the reason that we use the tester individual is because it has a known genotype, only little a's and only little b's. So when we observe these F2 genotypes down here, we know, watch this, we know that a little a in each one of those individuals had to come from that tester parent, because we know the tester parent's recessive. It's homozygous recessive. It has to give recessive alleles. We also know that that tester parent contributed 1 little b to each of those F2 individuals. Everybody okay with this? So we know the genotype of this F1 parent, the tester. We know it's little a over little a, little b over little b. So when we see all of these genotypes, its offspring, we know that at least 1 little a and at least 1 little b came from the parent on the right. Okay? What's left here in this circle? What letters are left? What does this tell us? These are alleles that had to come from which parent? other one. The dihybrid. This is how we know what sort of gametes, which we didn't know. That's what we're asking. The big question mark. What sort of gametes is the dihybrid producing? Down here, across the top of the Punnett square, this is the expected F1 gametes. We expect that F1 individual, the dihybrid, to produce exactly 1-to-1 to 1-to-1 ratios of the 4 different haplotypes. What we're trying to figure out is, what is that F1 individual actually producing in its gonad when gametogenesis is occurring? Is recombination occurring? Are we going to see a 1-to-1 to 1 ratio? So what's left here, I'm circling in blue, those are the haplotypes of that F1 dihybrid. So in this case, this dihybrid made 250 big A, big B, 250 little a, little b, 250 of each of the 4 types. So we can figure out, without actually taking the F1 dihybrid and opening up its gonad and taking out its gametes and genotyping them, we can figure out what the haplotypes are by simply letting the F1 mate with a partner, taking their offspring and genotyping their offspring. We can infer, as we did up here, by crossing out the known genotype of the tester, we can figure out what and how many of each type of haplotype the dihybrid produced. So we can fill in this question mark. What are the F1's haplotypes? So the parental types are the gametes that the 2 P0 individuals produce. A big A with a little b, that's parental, and a little a with a big B, that's parental. So which of these 4 types that the F1 dihybrid could produce, which of those are recombinant? Big A with little b and little a with big B are parental. So that's a parental type. That's a parental type, the bottom 2. But the parents' gametes never had a big A with a big B or a little a with a little b. So those are recombinant types. Just for this cross. How many recombinant, what's the fraction of recombinants? Of all of the F2s, how many were fertilized by recombinant gametes? There were 250 big A, big B gametes that were used to produce these F2s, the 250 F2s. 250 little a, little b gametes there, so half. 250 of this type, 250 of that type, 500 recombinant out of 1,000 total. So let's do the chi-square test, assuming that we observe exactly what we expect. What's going to happen? What is a chi-square test? What's the answer when you observe, set up this cross and you observe exactly what you expect? What should the p-value be? Should be p greater than 0.05, right? Really 0.05. P really small means significant difference. When you're observing the expected values are exactly the same, how big could a p-value get? What's the range of p-values? Smallest one's 0, the biggest one is 1. So p can be anything from 1 to 0, 100% probable or 0% probable essentially. So let's say those are our observations, and we had expected values that were exactly the same. We expect the Punnett square, 1 to 1 to 1 to 1, equal numbers of each of the 4 different genotypes. So both of the observed and the expected values total 1,000. We don't have to do the whole chi-square formula. Let's just do one clause. Take the top one. How many dihybrid genotypes, big A over little a, big B over little b, do we get? So you do observed, 250, minus expected, 250. What's that? 0. What happens when you square it? It's 0. What happens when you divide it by 250, the expected value? It's still 0. So every clause, when the observed and the expected values match, gives you 0. So in the end, the calculation becomes, after you fill in those 4 clauses for each of the 4 genotypes, you get 0 plus 0 plus 0 plus 0, which gives you a chi-square value of 0. When observed and expected values match, when you see exactly what you would have predicted, when genes are unlinked, where does chi-square value of 0 fall in this table? On the far left. In fact, there's only 1 0 up here. That's for a degree of freedom of 1. This is degrees of freedom of 4 minus 1, or 3 different genotypes. So you don't even see it on this chart, but basically, that's a p-value of greater than 0.995. For 0, p equals 1. So when observed and expected values match, the p-value is 1. There is absolutely no difference, but you knew this. I probably should have asked you this in the first place. Are these observed and expected values different, do you say? Of course they're the same. All of them are the same number. So we've just defined how to interpret a chi-square test. If you're ever confused about, wait a second, was it less than 0.05 or greater than 0.05 is similar? Do a quick little jot it down on a piece of paper. Do one chi-square test where you say, okay, I'm going to make the observed and expected values the same. Chi-square value is 0, you look it up on the table, it's, oh, okay, P1. So when I know that the observed and the expected values match, that gives me a big p-value. Therefore, it must be when the p-value is really small, it's when we know that they differ, the observed and the expected values. So in this case, observed and expected are not different. This is what you get for unlinked genes. Observed and expected values match. Now, let me go back for a second here. So when you do something like that, 250 big A, big B, and 250 little a, little b, those are the recombinant types, divided by 1,000 total. That gives us one measure of genetic distance, how far apart the genes are in the genome, on chromosomes. So 500 out of 1,000, 0.5. That's a value called the recombination fraction. Aptly named, it's the fraction of gametes that are recombinant. Recombination fraction, RF sometimes. 0.5. This is one of 3 ways that we'll represent genetic distances in class. What are the other 2 measurements of genetic distance? So one's got Morgan in it. Everything's got Morgan in it. So if you multiply recombination fraction by 100, that gives you 50 centiMorgans, CM, capital M, If you do lowercase m, that's centimeters, and that's not a unit of genetic distance. CentiMorgans. So recombination fraction of 0.5 means exactly the same thing as me telling you that two genes are 50 centiMorgans apart. It means that half of the gametes were recombinant, half are parental type. There's one other term that geneticists use, MU, or map units. It's exactly the same as centiMorgans. I have no idea. I apologize. I might someday say map units instead of centiMorgans. We don't really need 3 different units for describing exactly the same thing, but we have them. It's recombination fraction, multiply that by 100, and you get centiMorgans or map units. So recombination fraction, centiMorgans, map units. Convert them by either multiplying or dividing by 100, depending on which way you're going. We always start off calculating recombination fraction. I have no idea why I put this slide in here. We already did this. But it asks an important point. So this is a summary slide. When genes are unlinked, when they're on totally separate chromosomes, what fraction of the gametes should be recombinant? Based entirely on this Punnett square, Punnett rectangle. So here we have the tester gamete, only little a's and little b's. You put the dihybrid gametes across the top, and you get a 1-to-1 to 1-to-1 ratio. These types of F2 offspring. You cross out the tester's contribution to those F2s, and you're left with the F1's haplotypes. So we know that that F1 individual contributed those alleles to each of those individuals. 50% recombinant, 50% parental. When genes are on separate chromosomes. This is just based on Mendelian genetics, Mendel's laws. If genes are on separate chromosomes, they do his second law, they assort independently, which means half of the gametes get big A with big B, something that's parental-like, and half of them get big A with little b, something that's recombinant. So unlinked, bottom line, unlinked genes should expect to see 50% recombinance. What's that in centiMorgans? Half of your gametes are recombinant. What's that in recombination fraction? Fraction. Yeah, 0.5. So 50%, that means 50% of the gametes are recombinant. 50 centiMorgans, 50 map units, 50% recombinant gametes. This is what you're looking for to know that two genes are on separate chromosomes. You observe what you expect based on Mendel's second law, independent assortment. So unlinked genes, 50 centiMorgans. On the other hand, what's the other extreme? So you've got either genes that are on totally separate chromosomes, they assort independently at meiosis, you get random combinations of alleles in gametes, you get a 1-to-1 to 1-to-1 ratio in this cross. What happens when genes are perfectly linked? So today I'm just walking you through the two extremes of genetic mapping. One is genes are on separate chromosomes, you calculate 50 centiMorgans distance. Half of the gametes are recombinant, half are parental types. What happens when they're perfectly linked? So help me out really quick and then we're done. What are the gametes that are produced by those two P0 individuals? What are their haplotypes? Exactly like last time, there's just a slash instead of a semicolon. There's still a big A and a big B there, and there's still a little a and a little b there. Now they're linked though, right? There's no character in between the A and the B. There's no semicolon, no slash between them. Big A is on the same piece of DNA as big B. Same is true for little a and little b. So the tester gamete is exactly the same. In fact, these two are genetically identical individuals. So that's why, and I should have done this differently, that's why we have a little a, little b down there. No semicolon, my mistake. So what gametes can this F1 dihybrid, still dihybrid, it's still heterozygous at two different genes, they're just on the same chromosome. What sort of gametes can it make? If two genes are physically right next to each other on the chromosome, they always travel together, big A's with big B's and little a's with little b's. Through meiosis into gametes, they're never separated. You either get big A with big B, or you get little a with little b. That's what those letters next to each other means. They never get separated. You don't have independent assortment. You never have big A's with little b's or little a's with big b's. Genes are linked. In fact, in this case, I say perfectly linked. It means they're physically right next to each other on the chromosome. So when that random crossing over during meiosis happens, it never happens between those two alleles. It never separates them. So in this case, Punnett square doesn't actually have, we don't even need 4 columns. How many gamete types does that F1 dihybrid produce? It's either big A with big B, or it's little a with little b. When genes, this is a hypothetical case, when genes are perfectly linked, you get 0 recombinants. If we do that same thing, taking the tester genotype, haplotype here, little a with little b, we know that that contribution to the F2 genotypes from that parent, we can just cross out. We know where those alleles came from. Those little a's and those little p's came from the tester individual's gamete. So when we compare what's left, the F1's gamete haplotypes, which ones are there? Recombinant types or parental types? Remember, these are the parental types up here. The gametes produced by the parents, big A with big B, little a with little b. That's the only type of gamete that we see resulting from a cross when two genes are perfectly linked. So if it's all parental types and no recombinant types, what's the genetic distance that we calculate between these genes? Recombination fraction is something divided by the total. In this case, we've got a total of 500 F2s that we've looked at. So what divided by 500? What do we put on the numerator when we calculate recombination fraction? How many, recombination fraction? So how'd you get 0? It's 0. The number of recombinant types you saw. So how many gametes did we see that were big A with little b or little a with big B? 0. So we saw 0 recombinants. We looked at 500 total individuals. So what's the genetic map distance between genes A and B? 0. 0 recombination fraction. You multiply it by 100, you get 0 centiMorgans, 0 map units. So that's the answer to that question. Fraction of the gametes that will have recombinant haplotypes when genes are perfectly linked, when they're physically next to each other on the chromosome, is 0. So the range of map distances you can have, thanks for your patience, by the way, sorry. Range goes from 0 to 50. 0 map units to 50 map units. Linked to unlinked. Next time, we'll carry on.